Hi everyone, Dr. Burns here with our next lesson where we're going to be discussing the laws of thermodynamics as well as Gibbs free energy. So we've talked about entropy in our previous lessons, and we want to talk about now how it relates to both our system, so our chemical reaction, as well as the surroundings around that reaction, which we have referred to in the past as the universe. So, correctly predicting the spontaneity of a process requires us to consider entropy changes in both the system and the surroundings. So, an ice cube will spontaneously melt at room temperature when it's at 25 degrees Celsius. In this scenario, our system is the ice, and it has an entropy change that is positive. The surroundings are then everything else, which would have an entropy change that is negative, again following our first law of thermodynamics, where energy cannot be created nor destroyed, it can only be transferred. Since entropy is a type of energy, whatever entropy is utilized in the system is also then transferred to the surroundings in equal but opposite amounts. If we look at another scenario where we have a cup of hot water that is going to spontaneously cool down to room temperature, here our system is the hot water, and it has a delta S of negative. It's decreasing its temperature, becoming more ordered in how fast the molecules are moving, so it has a delta S that is negative. The surroundings then have a delta S that is positive. So while both of these scenarios are spontaneous at room temperature, they have different signs of S. So while delta S is a good indicator of a spontaneous process, it's not always going to tell us exactly if something is going to be spontaneous or not. We have to take both the system and the surroundings into account. So that brings us to our second law of thermodynamics. In a previous chapter, we've talked about the first law of thermodynamics that said that energy cannot be created nor destroyed. The second law then tells us that the change in entropy of the surroundings is directly proportional to the enthalpy of the system. So we can identify the change in entropy of the surroundings by the equation delta S of the surroundings is equal to negative delta H of the system divided by the temperature. Remembering that we have a difference between system and surroundings here, and delta H is enthalpy. A note I would also like to make is we typically see enthalpy in units of kilojoules, whereas entropy usually has units of joules per Kelvin. So we're getting the joules portion from the enthalpy, however it is in kilojoules, so you most likely have to do some sort of conversion. The Kelvin is coming from the temperature in our denominator of this calculation. So just keep that in mind. We want to keep our units in mind. We just want to make sure that they are all in the same energy unit of joules. Therefore, the second law of thermodynamics states that for a process to be considered spontaneous, it's the change in the entropy of the universe that must be positive to tell us if it is spontaneous or not. When we looked at our previous examples, the delta S of the system was what we were specifically looking at that had different signs, and therefore the signs of the delta S of the surroundings were also different. But now we want to look at, in order to predict if a reaction will be spontaneous, not only the entropy of the system, but also of that of the surroundings, which when we add them together is the entropy of the universe. So if the entropy of the universe is positive, then the reaction is spontaneous. So let's look at that in table form. Based on the second law of thermodynamics, the delta S, the change in the entropy of the universe, is equal to the change in the entropy of the system plus the change in the entropy of the surroundings. If the delta S of the universe is positive or greater than 0, then this will be a spontaneous process. If the delta S of the universe is less than 0 or negative, then it will be a non-spontaneous process. And finally, if the delta S is equal to 0, then this process is at equilibrium, which we haven't discussed yet, but we will in a future chapter. So how do we actually calculate the delta S of the universe, the change in the entropy of the universe? Well, we know that it takes into account the change in the entropy of the system and the change in the entropy of the surroundings. In a previous lesson, we've talked about how to find the change in the entropy, specifically of the system or of the reaction. The system and the reaction are the same thing. So we know that the delta S of a reaction is equal to the sum of the entropies of the products minus the sum of the entropy of the reactants. So if we know the reaction, we can find our delta S values for the system using Appendix 2, or the ALEKS data tab. We were also given an equation on our previous slide of how to find delta S of the surroundings. If we know the delta H of the system, so of the reaction, and we know the temperature, then we are able to find the delta S of the surroundings. We know that we can find delta H of the reaction, or of the system, because it's going to be very similar to our delta S, where we're going to take the sum of the enthalpies of the products minus the sum of the enthalpies of the reactants, again, which we can find from Appendix 2. So those are all constant values for the products and the reactants, and the temperature would be given to us in the problem, and it's most likely 298 Kelvin or 25 degrees Celsius. So if we're able to calculate delta S of the reaction and delta S of the surroundings, we can put both of those in and solve for delta S of the universe. And that will then be able to tell us if the reaction is spontaneous. So let's practice that. For the reaction in the table, we want to calculate delta S of the reaction and delta S of the surroundings, and then determine if this reaction is spontaneous at 25 degrees Celsius. So there's our temperature. Let's highlight that while we read it. So we're given some thermodynamic properties in our table here. This does come from your ALEKS homework, and you're given a few more reactions in the problem that you'll be getting. So remember, if the reactants or products are not in this table, you can also look in Appendix 2 or in the ALEKS data tab to find the values that you will need. So I have the reaction here, 2NaClO4 goes to 2NaClO3 plus oxygen, and we want to find delta S of the reaction, delta S of the surroundings, and then we need to determine if it's spontaneous, and the only way to do that is to find delta S of the universe. So let's go ahead and start solving for this. The first thing that we're going to solve for is delta S of the reaction. We've calculated these in the past, and we know that delta S of a reaction is equal to the sum of the entropies of the products. So our product is 2NaClO4, so 2 times the entropy of NaClO4, or ClO3 I should say. So that would be 123.4 plus the entropy of oxygen gas. Remember that entropy, every compound and element has a value for entropy, which is given here as 205.2. We then subtract off the entropies of the reactants, which in this case is 2 times that of NaClO4, which is 142.3. So let's grab our calculators so that we can work on this problem together. So we'll take 2 times 123.4 and add to that 205.2. And then we will subtract off from that 2 times 142.3. Double check my addition subtraction, make sure I got that right. So we have a delta S of the reaction of positive 167.4. And that's going to be in joules per mole Kelvin. So that's our answer for our first portion of the problem. Next up, we want to find delta S of the surroundings. If we look at our equation for that, delta S is equal to negative delta H of the system divided by the temperature. Well, we know the temperature is 25 degrees Celsius, but we have to convert that to Kelvin since S has units of joules per Kelvin. So we have to add 273.15 to that. So we get 298.15 Kelvin as our temperature. Now in order to find delta H of the system, we're going to do the same thing that we did with delta S of the system, except we're now going to use our values in the delta H column. And we have to note here that our units are in kilojoules per mole. So we are going to have to convert that. You can do this at any point. You can either convert them before you use them as an H value, or you can convert it after you found the delta H value. Before or after doesn't matter. It's really up to you if you want to convert it before or after. So let's see, let's calculate delta H. So delta H of the reaction is set up in the very same way, 2 times that of the reactant, NaClO3, which is negative 365.8. And now because this is enthalpy, back from our previous chapter, oxygen does not have a value of enthalpy. So you have to remember that that would be 0. Then we'll subtract off 2 times that of NaClO4, which is negative 383.3. So we got to make sure we get our negatives correct here. So we're going to take 2 times negative 365.8, and we're going to subtract from that 2 times negative 383.3. And we get a positive 35 as our answer. And that is in kilojoules per mole. So before we can use it to plug into our delta S, we do have to convert it. So we know that in 1 kilojoule, there's 1,000 joules. So we'll take that 35 and we'll multiply it by 1,000. So this is actually 35,000 joules per mole for delta H. So we can now use this delta H and plug it in to our equation for delta S of the surroundings. So we get delta S of the surroundings is then equal to negative delta H, negative 35,000 joules per mole, divided by the temperature, which was 298.15 Kelvin. So we get negative 35,000 divided by 298.15. And we get out negative 117.39 joules per mole Kelvin. So that is the delta S of the surroundings. So we will now use the delta S of the reaction and the delta S of the surroundings to solve for delta S of the universe. So delta S of the universe is equal to delta S of the reaction, positive 167.4, plus the delta S of the surroundings, negative 117.39. So we take 167.4, we add to that negative 117.39, and we get out positive 50.01 joules per mole Kelvin. So based off of the chart that we looked at earlier on the second law of thermodynamics, if the delta S of the universe is positive, then this is a spontaneous process. So when the question asks, is the reaction spontaneous at 25 degrees Celsius, we can answer yes, because this value is positive. Finally, we have the third law of thermodynamics. And the third law of thermodynamics is a simple one. It states that the entropy of a pure, perfect crystalline substance at 0 degrees Kelvin is 0. So when we're at 0 Kelvin, that means that there is no molecular movement. If there's no molecular movement, then there's no disorder in the system. So it is perfectly ordered when we are at 0 degrees Celsius or degrees Kelvin. Therefore, at 0 Kelvin, there is only one possible microstate, which is our W. Remember, a microstate is equal to W. So if we plug 1 in for W into our entropy calculation that we learned in our previous lesson, the natural log of 1 is 0. So that gives us an entropy of 0. The third law is what allows us to have entropy values for specific elements and compounds. And this is why elemental forms can have an entropy value, whereas they don't have an enthalpy value. It's because they have some sort of physical state. Their atoms are going to be moving in some way, even in their elemental form. So in some ways, they have disorder to them. The only time that an element or compound will not have any disorder is when it is at 0 Kelvin, and there is absolutely no molecular movement. Anything above 0 Kelvin, there is molecular movement, therefore there is some amount of disorder or some amount of entropy. So in order to talk more about the spontaneity of a chemical reaction, we do have to introduce yet another thermodynamic property, and that is the Gibbs free energy. The second law of thermodynamics, as we just saw, requires a measurement of the change in entropy of the system and the surroundings, which is not always possible. If you think about it, the surroundings is the entirety of the universe outside of the reaction that you're looking at. If we're trying to measure minute energy changes from a chemical reaction, we can't really measure the change in the entropy of the entire universe because it's so large in comparison to how small that change in the entropy will be. So it's really the measurement of the entropy of the surroundings, which is the difficult part. So instead, we are going to introduce a new thermodynamic property that can be used to relate the entropy of the system and the enthalpy of the system in order to predict the spontaneity. And this is called the Gibbs free energy. We denote the Gibbs free energy with a capital G, G for Gibbs, and it's also sometimes just referred to as the free energy. We can see the relationship between entropy and enthalpy in our equation for Gibbs free energy, where the Gibbs free energy, G, is equal to the enthalpy minus the temperature times the entropy. So G is equal to H minus TS. Our typical units for our Gibbs free energy are kilojoules. So we'll make this note a couple of times as we go through our practice problems, but just to start us off, we normally have Gibbs in units of kilojoules. I'm talking about what is given in our appendix, Appendix 2, or in our ALEKS data tab. Gibbs free energy is always given in kilojoules. Enthalpy is also given in kilojoules. But in Appendix 2, the S is given in joules, specifically joules per Kelvin. So we need to convert it to kilojoules per Kelvin before plugging in. Okay, so before we plug anything into this equation, everything needs to be in kilojoules, units of kilojoules. The Gibbs free energy is a form of energy, therefore it is a state function. So we can rewrite our equation for the Gibbs free energy using our deltas. Since it's a function of enthalpy and entropy, which are also state functions, we can say that delta G, the change in the Gibbs free energy, is equal to delta H, the change in the enthalpy, minus the temperature times the change in the entropy, delta S. Now, even though temperature is a state function, it's not a state function of energy, therefore it is remaining constant when we're looking at finding the Gibbs free energy. So, when we're talking about the Gibbs free energy, we are strictly talking about the system. Okay, as we said earlier, we can't easily measure these types of things, changes in the surroundings. We can only measure that of the system. So, just to make a note of this, the delta G, the delta H, and the delta S are all referring to the system, but we will not be using the subscript sys, system, on any of these from here on out. We will not be showing it because we no longer consider the surroundings when looking at the Gibbs free energy. We can use the Gibbs free energy as a more reliable indicator of spontaneity because there is a relationship between the Gibbs free energy and our previous spontaneity indicator, delta S of the universe. So that relationship is that delta G is equal to negative T delta S of the universe. And we said if we know the delta S, we can know if it's spontaneous or not. However, we said that it's kind of hard to measure the delta S of the universe since we'd have to find the surroundings. So we're doing this using our Gibbs free energy. So how do those relate? How does delta G and delta S of the universe relate to each other? Well, we talked about this earlier. If the delta S of the universe is positive, then the delta G is going to be negative because of that negative sign right there. It's going to flip-flop. So if the delta S is positive, delta G is then going to be negative, and the reaction is then going to be spontaneous. If delta S is negative, then delta G is going to be positive. Again, they're opposites of each other. And the reaction overall is going to be non-spontaneous. And whenever both of these are at 0, so delta S is at 0, delta G is at 0, then we say that the reaction is at equilibrium, again, which we'll learn about more so in a future chapter. So before we jump into some practice utilizing our Gibbs free energy, let's discuss why we say that Gibbs is free. Where did this free come from? Why don't we say free enthalpy or free entropy? Well, free energy provides information about the amount of work, W, which we haven't talked about in a while, but it was in our previous lessons, that can be accomplished by the spontaneous process. So in our free energy equation, the delta H tells us the energy that is produced by the process, and the T delta S portion tells us the energy that is lost to the surroundings. So it tells us how much we made from the process and how much was given off during that process. Therefore, the difference between the energy produced and the energy lost is then free energy to use in the process. It's the remaining energy that is used in that process. So it's free to do whatever it wants, specifically the amount of work it relates to that work. So since we're looking specifically at the sign of delta G to tell us if we are going to have a spontaneous versus a non-spontaneous process, well, delta G is related not only to the sign of delta H and the sign of delta S, but we also have to take the temperature into account. So we have a nice chart that kind of brings all of that together that tells us, well, if our sign of one of these is positive and the other one is negative, is this going to be spontaneous? Because it's now two factors that are going to affect the spontaneity. The enthalpy and the entropy come together to tell us about the Gibbs free energy, but the temperature is still going to contribute as well. So we have this chart. You are given this chart on your exams, so please practice using this when you're doing your homework. So along the top we see our values of delta H, our values of delta H along the top. We see that if delta H is positive, then this is endothermic. If delta H is negative, that is exothermic. And along the sides we see a similar setup, but now for entropy. So delta S is positive, that's an increase in our entropy, and delta S is negative, that's a decrease in our entropy. And now what we can do to tell us if what the sign is going to be of our delta G is we can compare those signs. So if we know our delta H is positive and our delta S is positive, well, we see where those two pieces come together, where they meet up. So they meet up here in this first square. And it tells us that delta G is going to be negative at higher temperatures and delta G is going to be positive at lower temperatures. And therefore the process is going to be spontaneous at higher temperatures. We'll talk about how to determine higher versus lower temperatures later on in this lesson, but it is going to be important to notify the distinction between differences in temperatures. Again, this was what I was saying before, where the temperature still plays a role. Then we have if delta H is negative and delta S is positive. This is going to be delta G is always going to be negative at any temperature, regardless of what that temperature is. Delta G is always going to be negative. Therefore, the process is going to be spontaneous at any temperature. If we look at the opposite, where delta H is positive and delta S is negative, then we see that delta G is always going to be positive and that this is going to be non-spontaneous at any temperature. And finally, if we have delta H and delta S both negative, then we see that delta G is going to be negative at low temperatures now. So see how we've swapped, went from high to low and low to high. So delta G will be positive at high temperatures. Therefore, the process will only be spontaneous at low temperatures. So let's practice using this. For the reaction, A plus B goes to product C. We know that delta H is positive 30 kilojoules and delta S is positive 50 joules. Therefore, this reaction is what? Use those values to determine if this reaction is going to be spontaneous at all temperatures, non-spontaneous at all temperatures, or spontaneous at either low or high temperatures. So here our units don't matter because even if we converted joules to kilojoules, our number is still going to be positive for S and positive for delta H. So if delta H is positive and delta S is positive, then we're going to have something where the reaction is spontaneous at high temperatures only, so our answer there is D. So we just want to keep practicing using that table in order to help us predict if the reaction is going to be spontaneous or non-spontaneous and if the temperature matters. So let's move forward with finding values for our Gibbs free energy. So given the following equation or chemical reaction, and what you recall from our previous chapter 10 and earlier in chapter 15, think about how you would calculate the standard free energy change, or the Gibbs free energy, for the following reaction. So we have C2H6 reacting to form hydrogen gas and C2H4. What information do you need to solve this problem? So since we have a balanced chemical equation, we could find our delta S and our delta H from our appendix 2. And if we know delta H and delta S, we can calculate delta S and delta H. And as long as we're given a temperature, we can use those to find our delta G. Right? We've solved this before. We found delta H. That was chapter 10. We've solved for delta S. We've done that earlier in chapter 15. So we're just bringing those two concepts together to solve for delta G. So let's solve this problem. I've given you the delta H and the delta S for this problem. So what I want you to do is calculate the delta H, calculate the delta S, utilize the temperature that I've provided over here, and solve for our delta G. So we're going to do this in a couple of steps. First, we're going to find delta H, then we'll find delta S and plug those in to solve for delta G. So in this reaction, we have our product. So the H of hydrogen is 0, so we don't need to worry about it. And C2H4 is 52.4. We'll subtract from that our reactant, C2H6, negative 84.0. So let's grab our calculators out so we can solve this problem together. So we'll take 52.4, subtract negative 84, and we get a delta H of 136.4 kilojoules per mole. We'll do the same thing for delta S, remembering that hydrogen will now have a value for enthalpy, so it'll be 130.57 plus C2H4, 219.5, and we'll subtract off that of C2H6, which is 229.5. So we'll take parenthesis 130.57 plus 219.5 and subtract off 229.5. So we get a delta S of positive 120.57, but that is in joules per mole, Kelvin. So we need to convert that S like we were talking about before. You will always have to convert your value of S to kilojoules if you are going to use it in the Gibbs free energy. So we are just going to divide this by 1,000 in order to get kilojoules. So we get that delta S is equal to 0.12057 kilojoules per mole Kelvin. And now we can plug those values in. So we can plug in our delta H and our delta S in for delta G. So we get delta G is equal to delta H 136.4 minus the temperature 298 Kelvin times the delta S 0.12057. So we get 136.4 minus 298 times 0.12057. So we get a delta G that is 100.47 kilojoules per mole. This is a positive delta H, so this would be non-spontaneous. So again, this is just taking in what we've learned previously about delta H and delta S, and we're using that to apply and solve for delta G. Now there are actually two ways to calculate our Gibbs free energy. The first way is the one we just practiced, where we utilize our knowledge of delta H and delta S. But that is going to vary, this delta G is going to vary with temperature. The second way is, if you've looked at your Appendix 2 or your ALEKS data tab, you see that there's a third column that's devoted to delta G values, or delta G of formations. So we can use our standard free energies from Appendix 2 and plug it into the same type of equation that we use to solve for delta S and delta H, where we take the G of the products and subtract off the sum of the G's of the reactants. So just like we did in our last problem, but instead of using H values and S values, we use G values. The only thing that's important to note about those delta G's of formation from Appendix 2 is that they are only for 298 Kelvin. So only if the reaction is at 298 Kelvin can you use the delta G's of formation. If you have a different temperature, if you need to have this happening at a different temperature, then you can use the first equation where temperature is allowed to vary. So let's look at the same equation, the same reaction we just did, now using our delta G's from Appendix 2. And we want to know, are the two variables calculated for the free energy, are they comparable to each other? And a note that I want to just make is Gibbs free energy values for anything in their elemental state is going to be 0 kilojoules, just like we saw in enthalpy. So the only things that have values for thermodynamics in their elemental state will just be for entropy. And when in doubt, just look at Appendix 2 or your ALEKS data tab. If there's a 0 there, then you know that it's its elemental form and it has no value for enthalpy or Gibbs. And if you're just want to double check, you'll see that there is an entropy value for all of those as well. So we do delta G of our products, which is just C2H4. So C2H4 is 68.4 minus that of C2H6, which is negative 32.0. So we get 68.4 minus our negative 32.0, and we get 100.4 kilojoules per mole, which is almost exactly what we had in our previous answer. We just have a few more decimal places due to the fact that our enthalpy and entropies had a few extra decimal places in them as well. But really, when it comes down to rounding and those minor changes, they're basically the same. So they are comparable to each other. Now in our chart of delta H and delta S and how those related to delta G and if it was spontaneous or not, we said that at high temperatures versus low temperatures would change the spontaneity for two of those situations. So what we can do is we can calculate the temperature at which the spontaneity of a reaction is going to change from spontaneous to non-spontaneous or vice versa. And for this, we have to bring in the fact that when we go from spontaneous to non-spontaneous, we're going through 0. delta G is changing from a negative to a positive, and the only way to do that is to go through 0. So at 0 is when we are going to change from spontaneous to non-spontaneous. So if we take our delta G equation and set delta G to 0, we can rearrange this equation now to solve for T. And that T that we solve for will then tell us the temperature at which we change from spontaneous to non-spontaneous. So that rearrangement is shown below, where T is equal to delta H over delta S. And again, that delta H and that delta S could be given, or you would have to solve for that using our thermodynamic values of entropy and enthalpy. So let's practice that. At what temperature is the following process spontaneous at 1 atm? So we have bromine going from a liquid to a gas. Delta H is defined as 31.0 kilojoules per mole, and delta S is defined as 93 joules per mole Kelvin. So we can plug that into T is equal to delta H over delta S. However, the first thing that we're going to have to do is change our units accordingly. It doesn't matter which units we change. We could change delta S to kilojoules, we could change delta H to joules. It doesn't matter. That energy unit is going to cancel out anyways because we're looking for a temperature in Kelvin. So as long as those energy units are the same for both H and S, it doesn't matter which one you convert. Now I want you to get in the habit of converting delta S, so let's take delta S and let's convert that, just so that we're continuing to get in that habit. So 93.0 joules per mole Kelvin, we're going to divide that by 1,000 to get kilojoules. So that's going to give us 93 divided by 1,000, 0.093 kilojoules now per mole Kelvin. So we can plug in our two values, our delta H of 31 kilojoules and our delta S of 0.93. So the temperature is going to be equal to delta H 31.0 over delta S 0.093. So delta H has units of kilojoules per mole. Delta S has units of kilojoules per mole Kelvin, so we can see that our kilojoules and mole units are all going to cancel, and we're going to be left with units of Kelvin in order to get a temperature. So we'll take 31.0 and we'll divide that by 0.093. And we get a temperature of 333 Kelvin. Now the next part of this question asks, if the temperature were to increase, would the process still be spontaneous? This is where we have to look at our table. So we have a delta H and a delta S that are both positive. So we are looking at this portion of the chart right here. We know that this process is going to be spontaneous at high or higher temperatures. And we know that that temperature that will denote whether we're going from spontaneous to non-spontaneous is 333. So if the temperature were to increase, so if I were to go to 334 Kelvin, since this process is spontaneous at higher temperatures, then this would still be spontaneous. So 333 is the flipping point for that. If, in this example, we had a delta H and a delta S that were both negative and we were in this box instead, and the question still asked us if the temperature were to increase, would the process still be spontaneous? Since this process, when they're both negative, is spontaneous at low temperatures or lower temperatures, if I were to increase the temperature, then it would be non-spontaneous. So again, you have to think about the wording, not only of what's in the box, but how that relates to the question that's being asked as well. Okay, so for our last two practice problems, I just want to practice putting together our concepts of delta H, delta S, and delta G, and how they can relate to each other, as well as tell us about spontaneity. So for the following reaction, use the values given to determine the unknown thermodynamic variable. Then determine if the reaction is spontaneous or not based on the Gibbs free energy. So this is a two-part problem. We first want to solve for delta S, and we also want to determine if it's spontaneous. We can determine if it's spontaneous without having to solve for delta S because we already know our delta G. Since the delta G here is negative, then we know that this reaction is spontaneous, because delta G, when it's negative, is spontaneous. We don't have to take the temperature into account because we have a physical numerical value of delta G. So now let's work to solve for delta S. So we know our equation is delta G is equal to delta H minus T delta S. We can go about this multiple different ways. You can rearrange your equation and then solve for delta S. You can plug in your values, simplify, and then solve for delta S. Whatever you prefer is fine by me. You just gotta make sure you're getting your signs correctly. I personally like to rearrange my equation before I plug my values in. First, so I don't make a sign error, and second, just to make sure that I'm getting everything in the right spot. So if I'm wanting to solve for delta S, I'm going to want to isolate it on one side of my equal sign. So I'm going to subtract off delta H, and I get delta G minus delta H is equal to negative T delta S. In order to isolate delta S, I'll divide both sides by negative T. So I get that delta S is equal to delta G minus delta H over negative T. So now, since I have all of those variables given to me in the problem, I can solve for delta S. Now we have to remember that T is given to us in degrees Celsius, and we need it to be in Kelvin. So we want to add 273.15 to that. So we get 117 plus 273.15. And we get 390.15 Kelvin. Okay, so now we're ready to plug everything in. Delta S is equal to delta G, negative 35, minus delta H, which is 12, divided by negative T, which is 390.15. So let's solve. Negative 35 minus 12 divided by negative 390.15. And we get a delta S of 0.120466 kilojoules per Kelvin. Because our units for delta G are in kilojoules and our units for delta H are in kilojoules. Now we can take that delta S and we can multiply it by 1,000 in order to get it into its units of joules, which is what the problem asks us for. So we'll take that 0.120, we'll multiply it by 1,000, and our answer then becomes 120.4. And that is our delta S, and that's in joules per Kelvin. For our last problem, I want you to work on this one independently. So given the reaction below, calculate the following thermodynamic values. First, calculate delta H, then calculate delta S, and then use those values to calculate delta G. So try that independently now. So we'll solve for delta H and delta S just like we did in our previous problems and in our previous lessons. So delta H is going to be equal to the products minus the reactants in order to get, let's see, negative 484.3 minus negative 201.0 plus negative 110.52. So that gives us a delta H of negative 172.78, and that is in kilojoules per mole. For delta S, we'll do the same thing. So let's see, our product is 159.8 minus our reactant, 239.9 plus 197. So 159.8 minus 239.9 minus 1 plus 197.7. There we go. Which we get negative 277.8, and that is in joules per mole Kelvin. So we need to divide that by 1,000. Because what we're going to be doing is using that delta S to calculate delta G. So we need it in kilojoules. Okay, so now we'll use our two values of delta H and delta S, and we'll plug that in for delta G at 25 degrees Celsius, which is 298.15 Kelvin. So we get that delta G is equal to delta H, negative 172.78, minus the temperature, 298.15, times our delta S, negative 0.2778. So we get negative 172.78 minus 298.15 times negative 0.2778. We get a delta G of negative 255.6 kilojoules per mole. And since that is negative, this is then a spontaneous process.